Hello everybody, we are Group 8 and our topic is Mechanics of Stretchable Electronics. This will be presented by Fausto, Brian, Aaron, and Udit, and myself, Jair. So, to start off, mechanics of stretchable electronics is the ability for electronic devices or circuits to withstand mechanical deformation, like being stretched, bent, compressed, or stressed, or twisted, while still maintaining full function. They are important because this allows electronic devices to integrate between the human body, soft machines, and or any irregular surfaces. They can change industries and create new ways of safety and comfort. The industries who can benefit from the stretchable electronics include wearable medical devices, soft robotics, and stress sensors. As mentioned before, these stretchable materials and devices are engineered to endure a variety of mechanical loads while maintaining functionality. The mechanical loads these devices endure include uniaxial, biaxial, bending, flexion, and torsion. Some mechanical considerations when manufacturing such devices include strain distribution. Uneven strain can lead to localized failure, micro cracks at sharp corners, causing micro cracks at sharp corners. Elastic behavior. Materials will return to the original shape after release of stress for long-term durability. And fatigue resistance, critical for applications involving cyclic loading such as wearable medical devices. Some of the common conventional materials used in devices include intrinsically conductive polymers, carbon nanotubes, silver or metal nanowires, nanoparticles, and liquid metals. They are then paired with flexible support materials such as silicone-based elastometers, rubbers, and hydrogels. Polydimethylsiloxane is one of these substrates with soft biocompatible and easy to process substances. EcoFlex is another one with a highly stretchable silicone rubber. They are then used together with rigid conductive fillers to allow stretchable and flexibility. Choosing the right combination is very important for mechanical flexibility and electrical reliability.
Stretchable electronics are made possible through a few key structural design mechanisms. Let's take a look at the three of the most common. First, we have the wavy structural configuration. This method transforms stiff, thin films into flexible structures by forming hill-like waves that can expand and flatten when stretched. The degree of stretchability and compression is influenced by the amplitude and wavelength of these waves, giving engineers precise control over the material's flexibility. Next is the island interconnect configuration. Here, rigid islands, which could contain active electronic components, are connected using flexible interconnects, such as thin metal lines or bridges. This setup allows for significant and reversible deformation, particularly when strain is applied along specific directions, making it ideal for wearable and conformable devices. Lastly, we have kirigami or origami designs. Inspired by traditional paper, folding, and cutting arts, these approaches introduce intentional cuts and folds into rigid materials. This creative pattern enables those materials to stretch and bend in ways they couldn't naturally, expanding their functionality in dynamic and complex movements. Each of these mechanisms play a crucial role in pushing the boundaries of what's possible in flexible electronics.
Mechanical reliability under repeated deformation, fatigue and fracture. Stretchable electronics experience repeated cycles of stretching, bending, twisting, and compressing. Over extended periods, these repetitive mechanical actions cause fatigue, leading to microcracks, fractures, and eventual failure of components. Stress concentration. Areas with abrupt geometry changes, sharp corners, or interfaces between rigid and stretchable materials frequently experience elevated stress concentrations. These stress points significantly accelerate degradation and shorten the overall lifespan of the device. Real-world examples. Wearable sensors used for tracking continuous health or athletic performance often fail prematurely due to the repetitive stress from human motion. This limits their reliability and requires frequent replacement or redesign. Integration of contrasting materials. Material compatibility issues. Stretchable electronics frequently integrate rigid conductive components, such as metals and semiconductors, with elastic and compliant substrates like polymers or elastomers. Significant differences in thermal expansion, stiffness, and elasticity between these materials result in interfacial stresses, causing delamination, cracking, and degradation of performance. Adhesion and interface management. Achieving robust adhesion and durable interfaces between materials with vastly differing elastic moduli is both technically challenging and critical. Specialized adhesives, surface treatments, and advanced interface engineering techniques are often necessary to enhance bonding strength and maintain structural integrity during prolonged usage. Illustrative scenario. Electronic skin patches and wearable health monitors require exceptionally stable interfaces between silicone-based electronics and soft, stretchable polymer substrates. The capability of these devices to endure repeated deformation without interface failure directly impacts their safety, effectiveness, and user comfort. Maintaining functional performance during stretching. Electrical performance stability. Mechanical deformation due to stretching can significantly alter essential electrical properties such as resistance, capacitance, inductance, and overall signal integrity. Such changes can lead to unreliable or inaccurate device performance, limiting practical usability. Geometric design considerations. Engineers frequently utilize geometric designs, including serpentine structures, wavy patterns, and fractal geometries, to enable stretching and flexibility without drastically compromising electrical and mechanical performance. However, precisely optimizing these patterns to balance flexibility, durability, and electrical stability is intricate and challenging. Application insight. Flexibility displays, wearable sensors, and medical implants demand consistent and reliable electrical performance under extensive mechanical deformation. Achieving this requires meticulous material selection, sophisticated structural design, and thorough validation through rigorous testing protocols to ensure functionality and reliability throughout the product's life cycle.
One of the most important areas where stretchable electronics are making an impact is healthcare. Devices like electronic skin are ultra-thin, breathable sensors that stick to the body like a second skin, recording things like temperature, hydration, and heart rate. Then we have implantable devices. Traditional rigid pacemakers and probes can damage tissue, but stretchable versions move with the body, reducing inflammation and improving comfort. Even smart bandages can now monitor wound healing and send data in real time. These innovations improve patient care by being more adaptable, less invasive, and more accurate. Stretchable electronics are also transforming the world of robotics and wearable tech. In soft robotics, stretchable sensors allow robotic arms or grippers to gently grasp fragile items like fruit or glass. For prosthetics, the integration of pressure sensors enable wearers to feel and adjust their grip, improving control and safety. We also see this tech in smart textiles. Shirts or suits can track muscle activity or posture in athletes or patients. And for everyday fitness, flexible material in wearables like wristbands make devices more durable, water resistant, and comfortable to wear all day. Finally, in consumer and environmental sectors, stretchable electronics are already in use. You've probably seen foldable phones like the Samsung Galaxy Fold. These use stretchable OLED displays to bend without damage. Researchers are also working on stretchable batteries that can power these devices while staying flexible. In smart homes, stretchable sensors are embedded in walls or furniture to detect motion, temperature, or pressure, making automation seamless. And for sustainability, flexible solar panels can now be added to tents, backpacks, or jackets, allowing for more mobile power in off-grid situations. These real-world examples show how adaptable this technology really is.
As stretchable electronics move from experimental setups to real-world deployment, the research focus is rapidly shifting. We're seeing innovation converge across three major domains. First, physiological integration, where devices must mechanically and functionally adapt to soft and moving tissues. Second, intelligent materials that are engineered with AI-guided design tools to optimize for multifunctionality, durability, and resilience under strain. And third, the need for sustainable, scalable manufacturing. So these technologies can move beyond the lab into high throughput, eco conscious production pipelines. These directions are reshaping how we think about mechanical and electronic reliability under deformation. In the next slides, we'll explore specific breakthroughs that reflect this shift, beginning with advances in biomedical integration and adaptive material systems. Recent work at Stanford's Power Group has demonstrated intrinsically stretchable integrated circuits made from carbon nanotube semiconductors that are embedded in soft elastomers. These circuits are now small and fast enough to drive micro LEDs and power tactile sensors with sub-millimeter resolution, surpassing the sensitivity of skin. Because these devices conform to biological surfaces, they minimize tissue irritation and open the door for implantable electronics in brain, heart, and gut. At the same time, AI-driven material discovery is enabling faster, more efficient design of conductive composites. Machine learning algorithms are now being used to tune formulations like CNT elastomer blends for improved fatigue resistance and conductivity retention under strain. Yale's breakthrough, on the other hand, with biphasic gallium indium, has resolved one of the toughest mechanical problems, which is failure at the interface between soft, stretchable circuits and rigid electronics. Their nanoparticle based approach allows these materials to stretch and still maintain strong, stable electrical contact. Together, these technologies are enabling smart implants, neural interfaces, and adaptive prosthetics, bringing engineering closer to seamless human device integration. As we look toward real-world deployment, scalability and sustainability become just as important as performance. Organic photovoltaics, or OPVs, offer promising energy source for stretchable electronics. These are printable, lightweight, and non-toxic solar films that can be integrated into clothing, medical patches, or soft robotic skins, removing the need for bulky batteries. In terms of manufacturing, additive techniques like flexographic printing and inkjet deposition with conductive inks allow circuits to be directly printed on biodegradable substrates, reducing electronic waste. Structural and in-mold electronics embed circuits directly into curved 3D surfaces like automotive dashboards or prosthetic shells. This reduces part count and improves both durability and form factor. Roll-to-roll processing and transfer printing now allows for scalable production without sacrificing nanoscale performance. Moving forward, designing for disassembly, reusability, and energy autonomy will be essential to ensure these technologies are not only advanced but also sustainable and commercially viable.